Welcome to Demystifying Math. This is part 2 in a video series on graphing functions that have asymptotes. In this video we're going to be graphing the function f of x equals 4 minus 1 over x squared minus 1. Now the first thing that I want to do is rewrite this so it's one fraction. So I'm going to find my common denominator, which is x squared minus 1. So I'm going to multiply the 4 by x squared minus 1 and divide it by x squared minus 1. Then bring my two fractions together as 1. And then all I did was distribute the 4 and combine the constants. So I'm left with 4x squared minus 5 over x squared minus 1. Now you can factor the denominator, and that's going to help you figure out any values that are not in your domain. So in this case, x equals 1 and x equals negative 1 are not in the domain. When you have any values that are not in your domain, your graph could either head toward infinity or negative infinity as you approach those numbers, or it could head toward a specific number which causes a hole in the graph. If it heads toward infinity or negative infinity, you can have an asymptote at those values of x. So let's take a closer look at what happens as we approach 1 and negative 1. So we're going to plug in some values, first of all, that are very close to 1. And I chose 0.9, 0.99, and 0.999. And as you can see, as we close in on 1, the numbers are going toward positive infinity. And we're closing in 1 on the left side of it. So as we close in on 1 from the left side, the graph is going toward positive infinity. Let's look and see what happens as we close in on 1 from the right side. So we're going to plug in these three numbers, 1.1, 1.01, and 1.001. It looks like the numbers are heading toward negative infinity pretty quickly. So we're going to take the limit of that and call it negative infinity. And this is from the right side. So in this case, because we have the graph going to infinity and negative infinity, we know that we have an asymptote at x equals 1. Okay, let's see what happens as x approaches negative 1. So we're going to start off with negative 1.1, negative 1.01, and negative 1.001. As we plug those numbers into the function, you can see that the output values are going toward negative infinity. So as we approach negative 1 from the left side, the graph is going toward negative infinity. Let's go ahead and look and see what happens as we approach negative 1 from the right side. So we're going to plug in negative 0.99 negative, and negative 0.999. And these numbers are going off toward positive infinity. So again, we have an asymptote at x equals negative 1, because the graph is going to be unbounded as we approach that value. Now let's look for our horizontal asymptote, and we can do that algebraically. We're going to take the limit of the function as x approaches infinity. To do it algebraically, you're going to divide everything by x squared. I always divide it by the variable with the highest degree. That way it'll clear out a lot of numbers for you. So we're dividing each term by x squared. We end up with 4 minus 5 over x squared and 1 minus 1 over x squared. So if we take the limit as x goes to infinity, think about x as being an extremely large number, like 1,000,000. If you had 5 over 1,000,000 squared, that number is going to be extremely close to 0. And so would 1 over 1,000,000 squared. So for the 5 over x squared, that's going to head towards 0. And the 1 over x squared is also going to head towards 0. So we're left with 4 over 1, or 4, as our limit, which tells us that we have a horizontal asymptote at y equals 4. Once in a while what happens is you have a function that will cross its horizontal asymptote. Remember that when we're analyzing the graph to figure out where the horizontal asymptote is, we're only analyzing it as x goes to infinity. Of course, we could also analyze it as x goes to negative infinity, but you should get the same answer. Okay, so if it's closer to 0, not way out at infinity, the graph could do all kinds of things. It could cross its horizontal asymptote. So we always want to check and make sure to see whether it does or not. So what we're going to do is set our function equal to the y value of 4, which is where our horizontal asymptote is, and see if there's any possible solutions. So you have 4x squared minus 5 equaling 4 times x squared minus 1. Is that going to happen? Well, distributing the 4, we end up with 4x squared minus 1. And there's no way that you can take a number and subtract 5 and get the same answer by subtracting 1. So there's no possible solution here. Oh, in this case, the graph does not cross the horizontal asymptote. Okay, now that we have our asymptotes, let's go ahead and figure out on what intervals the graph is increasing or decreasing. And we can do that by taking our first derivative. We're going to let u equal our numerator and v equal our denominator, and then take the derivatives of both. Then we're going to plug into the quotient formula. So we're going to take the second times the derivative of the first and subtract the first times the derivative of the second and divide by this denominator squared. So we have 8x times x squared minus 1, which we're going to distribute the 8x, and then we're going to distribute the negative 2. And what you should notice is that the 8x to the thirds canceled each other. So we're only left with 2x in the numerator. Now you want to find any of your critical points, and that's going to be wherever your numerator is equal to 0 or where your denominator is equal to 0. So at negative 1, 0, and 1 we have critical points. Remember that at negative 1 and 1 we have vertical asymptotes, so our graph is undefined there. Well, we're going to go ahead and set up our number line with negative 1, 0, and 1 on it, and test a point in each interval. So below negative 1 I chose negative 2, and I got out negative 4/9. So that tells me that the graph is decreasing on the interval from negative infinity to negative 1. Then you have to choose a point between negative 1 and 0. I chose negative 1/2. And I got out negative 16/9. So it is decreasing again there. Again, remember that in between those two intervals of decreasing, there is an asymptote. Between 0 and 1, we want to test a point, so I chose 1/2, and I got out positive 16/9, which tells me that the graph is increasing on that interval. We have one more interval to check, and I chose to put 2 into that derivative function, and I got out positive 4/9, which means that the graph is increasing from 1 to positive infinity. Now at negative 1 and 1 they're asymptotes, but at 0 it's not. So that means that 0 must be a minimum point, because the graph is going from decreasing to increasing. So what we're going to do is plug in 0 into the original function, the f of x function, to get our ordered pair on our graph where we have a relative minimum point. And we got 0, 5. Okay, now we're going to look at the concavity of the graph, and we're going to do that by taking the second derivative. So we have our first derivative, which is 2x over x squared minus 1 all squared. Our numerator is going to be u, which is 2x, and our denominator is v, which is x squared minus 1 all squared. So the derivative of the numerator is 2, and the derivative of the denominator, we're going to have to use our chain rule on that one. So for the outer function, the derivative is 2 times x squared minus 1, and the derivative of the inner function is 2x. So that gives us 4x times x squared minus 1. Then we're going to plug into our quotient rule. So we're going to take the derivative of the first, or the numerator, times the v function, which is the denominator, and then go in the other direction. So we're going to take the u function and multiply it by the derivative of the v function, and divide by the v function squared. Then what I did was I factored out an x squared minus 1, so, and a 2. So I'm left with x squared minus 1 for the first term in the numerator, and for the second term I'm only left with 4x squared. And I'm just going to simplify that a little bit. So the x squared minus 1 in the numerator here canceled with one of these, so we now only have x squared minus 1 to the third. We still have the 2 here. And then inside the brackets here I would have a negative 3x squared minus 1, so I factored out the negative as well. So I have 3x squared plus 1. Now we want to find our critical points for our second derivative, and that's where either your numerator or your denominator is equal to 0. So 3x squared plus 1 can never equal 0. So we don't have to be concerned with those. So our only critical points are where our denominator is equal to 0, and that's going to be a plus or minus 1. So we're setting up our number line with those intervals from negative infinity to negative 1, and then from negative 1 to 1, and our third intervals from 1 to positive infinity. So we're going to test points in each interval. So when I tested the second derivative at negative 2, I got out a negative. So that tells me the graph is concave down on the interval from negative infinity to negative 1. Between negative 1 and 1, I have a 0 that I plugged in, and I got 2, so it's concave up on that interval. Then I plugged in a positive 2 and got out a negative, so it's going to be concave down from 1 to positive infinity. So now we have the concavity of our graph. We don't have any inflection points because in between the changes in concavity, we have asymptotes. Alright, so now all we need are a few more points to draw the graph. So I'm going to plug in negative 3, negative 2, negative 1/2, positive 1/2, 2, and 3. So I have a bunch of ordered pairs that I can plot. Alright, so you should try to go ahead and draw your graph. You want to draw your vertical and horizontal asymptotes first. Do that with a dotted line so you make sure that you understand that it's not actually part of the graph. Then you want to plot a few points between and beyond the vertical asymptotes. So we plotted several points over here, but you also want to plot the point that we found, which is a minimum point at 0, 5. On the right side of negative 1, you're going to draw a curve that's decreasing and concave down. Between the vertical asymptotes, you're going to draw a curve that's decreasing on the left side of 0 and increasing on the right side of 0 and is concave up. On the left side of x equals 1, you're going to draw a curve that is increasing and concave down. When you get done, come back and check your work. Alright, so you should have a graph that looks similar to this one. And check your work and see how you did. You can always pause the graph if you need to. Pause the video if you need to. Thank you for tuning in to Demystifying Math.